So let's start our webinar. Today, the speaker is Dr. Georgia Denolfo, who received her bachelor's degree from University of Chicago and then her PhD from Washington University in St. Louis. She has been at NASA Goddard Space Flight Center for over 20 years by now as research astrophysicist, and she is currently leading a wide range of research on the acceleration and transport of solar energetic particles, in addition to instrument development of charged and neutral particle detectors. She is also a deputy project scientist for ACE and stereo missions and the mission scientist for IMAP mission. So please, Georgia, go ahead. You have your 45 minutes for presentation.
Okay. Well, I wanted to thank everybody who's actually joined the webinar and also thank Eric Gregory for the invitation. So I'm excited to present some research about our group that was recently published where we explore the origin of long-duration gamma ray flares. So the defining feature of long-duration gamma ray flares is emission that is observed in the high-energy gamma rays with energies greater than 50 MeV that can last for tens of minutes to many hours. Dozens of long-duration gamma ray flares have been observed with the Solar Maximum mission and also the Compton Gamma Ray Observatory, and I recommend some excellent reviews by Chup and Ryan and Vilmer et al. Typically, the gamma ray emission can exceed several GeV in energy and is often delayed compared to the impulsive hard X-ray emission and microwave emissions. The high energy emission characteristically persists well after the emission has died down. And finally, the long duration gamma ray flares are strongly associated with coronal mass ejections, type 2 and 3 radio emission, and solar energetic particles. The origins of long duration gamma ray flares is still unknown, and the challenge to theory is to explain the extreme energies and the long durations. So it's generally accepted that these gamma rays are the result of pion production from protons and alphas with energies above the pion production threshold of 300 MeV for protons and 200 MeV for helium. A distinguishing feature of the pion decay channel is the characteristic Doppler broadened 69 MeV peak associated with the pi zero decay. So there are actually two compelling theories for the origin of long duration gamma ray flares that have received a lot of attention in the most recent publications. The first scenario attributes the production of gamma rays from protons that back precipitate from the CME driven shock. Of course, we know that shocks are accelerated to 1 AU. Indeed, we see them as solar energetic particles and also at higher energies, as in this figure down here. I don't know if you can see. Anyway, the figure down below, which is a neutron monitor figure showing ground level enhancements. We refer to this model as kind of a local effect in that the acceleration occurs at the sun. The other scenario considers the injection and acceleration of particles along large coronal loops that eventually precipitate to the photosphere to produce high energy gamma ray emission. Pitch angle scattering from magnetic turbulence may serve to further accelerate the particles. Large post-flare loops may serve as the possible structures for this acceleration and are observed in H alpha, but may not be visible in soft X-rays, making it difficult to precisely model these flares. We refer to this model as the remote effect in that the acceleration occurs at some distance from the sun. So there are other scenarios have also been considered. For instance, Ryan et al. Considered the possibility of particle acceleration in reconnection electric fields in active region flare loops formed behind the coronal mass ejection. However, recently Kaler et al. Examined this more closely and showed that the active region magnetic arcade formation is terminated well before the extended periods of the long duration gamma ray flares. The figure here is essentially showing that the reconnection timescales are much smaller than the long duration timescales. It is also hard to see how this model can account for the spatially extended emission associated with behind the limb events, which I'll talk about in more detail soon. So Hudson et al. Also proposed a lasso model in which acceleration occurs along open and closed magnetic field lines through a protracted loop structure that may extend out to several solar radio and that transports particles to the chromosphere and photosphere as it retracts, as might be the case for post-CME inward flows. Hudson points out that we can see hints of particle inflow with the 2014 September behind the limb long duration event. The first long duration gamma ray flare occurred in 1982, June 3rd. It was observed with solar maximum emission covering an energy range from 0.3 to 100 MeV. The impulsive phase lasted about a minute and was followed by an extended phase lasting about 15 minutes. The figure to the right here shows the X-ray emission beginning in the impulsive phase, and the middle panel shows the impulsive gamma ray emission and a subsequent peak corresponding to the gradual phase emission. This event was interesting as it also detected solar neutrons, as seen specifically in the bottom panel with neutron monitor data. The energy spectrum is hard and consistent with the decay of pions, shown in the figure to the left here. Finally, this event was associated with a fast CME and type 2 radio emission that suggested to Ramadi as early as 1987 that there was a possible connection with the acceleration of SEPs, perhaps at the CME shock. While we've known about long-duration gamma ray flares since Compton Gamma Ray Observatory and SMM, Fermi-LAT has really changed our perspective on these events. We now know that they're much more common. In fact, we've learned a great deal from the comprehensive work of Scher et al. In 2018, in which nearly 30 long-duration gamma ray flares were identified with Fermi-LAT data. The figure to the right here shows a typical time profile for these events. The Fermi-LAT observations are shown as the solid symbols, and the inset shows the impulsive phase in hard X-rays highlighted by the pink shaded region. The solid arrows delineate the CME onset, and the dashed arrow the onset of the type 2 radio emission. Several important conclusions can be drawn from the Scher et al. Work. I just want to highlight a few. The spectra of long-duration gamma ray flares appears to be consistent with the production of pions with a smooth exponential decay, which is consistent with the observations of the 1982 flare I discussed earlier. The extended emission also appears to be temporally distinct from the impulsive phase. There is also a strong association between the greater than 100 keV X-ray emission in the impulsive phase and the greater than 100 MeV gamma ray emission in the extended phase. And furthermore, to explain the gamma ray emission, we need a factor of 10 more protons in the accelerated, to be accelerated in delayed phase than in the impulsive phase. Finally, most of the long-duration gamma ray events are associated with CMEs, type 2 and 3 radio emission, and SEPs. Given the strong association with SEPs and CMEs, Scher et al. Concluded that the long-duration gamma ray flare emission is likely a result of back precipitation from CME-driven shocks. Indeed, his conclusions agree with a separate study of correlations between the long-duration gamma ray flares and other solar contextual data observations by Winter et al., 1983 publication. So radio data is also quite revealing. Gopaswamy et al. Found that long-duration gamma ray flare emission and type 2 bursts are highly correlated. The type 2 end frequency has an inverse linear relation with the duration of the long-duration gamma ray flare emission, suggesting that IP shocks remain strong over larger distances from the sun. In addition, the duration of the type 2 bursts and the long-duration gamma ray flare emission have a linear relationship, suggesting that the same shock is responsible for accelerating both electrons and protons. From these observations, Gopaswamy et al. Concluded that this was strong evidence for the back precipitation scenario for the origin of long-duration gamma ray flares. Several researchers have attempted to model the transport of particles accelerated at the shock back to the sun. Pocherov and others assumed an ideal radiomagnetic field from the shock back to the surface and showed that about 1% of the particles make it back to the solar surface, This is in part due to the reflections from mirror force. On the other hand, a more recent calculation, assuming more realistic magnetic configuration by Afanasieff, suggests that it is possible to get particle precipitation with higher rates. In this study, they modeled two specific events, the January 23rd and May 17th, 2012 events. These two events were chosen because one did not produce a GLE, while the other, specifically the May 17th event, did. Precipitation was modeled by combining a coronal shock model with a downstream propagating model, including diffusive downstream particle transport. So it's possible to gain even more insight on long-duration gamma ray flares by considering the cases where we observe high energy gamma ray emission, but the associated active region appears to be behind the limb of the sun. The first behind the limb long-duration gamma ray flare was the 1981 September 29 flare observed by SMM, which demonstrated that long-duration gamma ray flares can have quite large spatial extent by as much as 30 degrees. This event was also associated with the largest SCP event since 1956 with protons up to 20 GeV and also a fast CME. The association with the CME led Cliver et al. To hypothesize that the large spatial extent of the long-duration gamma ray flares could result from a CME that essentially helps to spread the protons to the front side of the sun. So Fermi-Lat also observed three long-duration gamma ray flares associated with behind-the-limb sources: the October 11, 2013, the 2014 January 6, and September 1st flares. These Fermi-Lat behind-the-limb events provided an important opportunity to examine the connectivity of the shock front to the solar surface as a means for enabling particle precipitation. So using the potential field source surface model and MHD modeling to identify the magnetic connectivity of the CME-driven shock to the photosphere, Plotnikov and Jen showed that the reconstructed shock fronts become magnetically connected to the visible solar surface just before the onset of greater than 100 MeV gamma ray emission as observed by Fermi-Lat. Jen also showed that a drop-off in the gamma ray intensity is observed just as the shock transitions to a quasi-parallel shock geometry. These modeling efforts clearly add support to the back precipitation scenario. So one important clue to understanding the origin of long-duration gamma ray flares is to compare the number of precipitating protons derived from gamma ray observations to the number of protons measured in space and presumably accelerated at the CME shock. Here I'm showing the first comparison of these two particle distributions by Scher et al., where they concluded that the number of precipitating protons varied between 0.1 and 50% of the numbers detected in space, suggesting that there are ample particles in space that could precipitate back and contribute to the long-duration gamma ray flare emission. So more recently, our group took a closer look at this calculation by taking advantage not only of the Fermi observations, but also another mission originally designed for astrophysics, but very successfully applied to heliophysics, the Payload for Matter and Antimatter Exploration and Light Nuclei Astrophysics PAMELA mission. PAMELA, as many of you know, was designed to measure galactic cosmic rays between several tens of MeV to several hundreds of GeV, but it is also quite sensitive to solar energetic particles over a broad range in energy from greater than 80 MeV to several GeV. Fermi-Lat, also designed to detect high energy gamma rays from astrophysical phenomena, has been extremely successful in detecting high energy gamma rays from the sun, transforming our picture of gamma rays and in particular long duration flares, as I've mentioned earlier. What's exciting here is that the ions producing the long duration gamma ray flare emission measured by Fermi are in the same energy range that was covered by PAMELA, making it possible for the first time to closely examine the question of the origin of long duration gamma ray flares. So we can gain further insight into the origin of long duration gamma ray flares by comparing the population that produces the high energy gamma ray emission with solar energetic particles, as was done by Scher et al. However, in this study, we take advantage of very sensitive measurements of PAMELA. PAMELA observed 26 SCP events over the course of its mission. Here we show the helio longitudes for the associated sources of each event. including the backside events, measured by Pamela, that's to the left. The red points show the events that were in common with Pamela and Fermi-Lat, and the blue points correspond to events for which Fermi only observed emission. And finally, the green points represent Pamela-only events. We were able to compute the spectra for 26 SEP events with Pamela. And what is important to notice here is that Pamela has enough statistics to carefully measure the spectra and has identified spectral rollovers for all events detected, shown to the bottom right here. And the spectral rollovers are consistent with fits to the Ellison-Ramadi functional form consisting of a power law with an exponential rollover. The universality of these rollovers suggests to us that the ground level enhancements, for example, that one that is shown here in aqua, are simply extreme ends of a continuous distribution of energetic particles, likely produced by the same acceleration process. Details of these calculations are discussed in our recent publication by Bruno et al. In 2018. But out of the 26 events that we observed, 14 Pamela SEPs are associated with greater than 100 MeV gamma ray emission as detected by Fermi-Lat. So using the Pamela spectra, we compute the greater than 5 MeV fluence based on the Ellison-Ramadi fits obtained from our SEP spectra. What you should notice, of course, is that it is important to account for the spectral rollovers when computing the total fluence above 500 MeV, highlighted here in the blue shaded region in the upper plot. To compute the total number of protons in space, we assume an isotropic flux and integrate over the spherical surface at 1 AU. We further assume that the particle spatial distribution is characterized by a periodic Gaussian. Integrating over the entire spherical surface reduces to a fairly simple form that depends on the particle spatial distribution and two important correction factors. The first correction accounts for Pamela's observation not being made on the IFM, the interplanetary magnetic field that connects with the peak of the particle distribution. And the second accounts for the particle transport effects such that there is a potential to overcount particles as they scatter multiple times within the spacecraft location. So the spatial distribution of SEPs in space is shown here and is determined by combining the event integrated intensity greater than 80 MeV from Pamela and both stereo A and B, and fitting these intensities to a periodic Gaussian function with respect to the connection angle between the spacecraft magnetic foot points at 30 RS, 30 solar radii, and the location of the parent flare. So this is just showing the SEP spatial distribution for all the events as a function of heliocentric Earth equatorial coordinates. The star represents the flare location, and of the magnetic foot points of Pamela and stereo are shown as the circle and triangles. Interestingly, you can see events where Pamela was well connected and observed to the peak intensities, but also cases where Pamela was not well connected at all, and yet we are able to observe greater than 500 MeV protons. So we also need to understand how the high energy SEPs are transported through the heliosphere. To do this, we can examine the dependence of spectral features on the longitude and connectivity. This is a familiar picture by Hilary Kane adapted for our Pamela results. Depending on how the spacecraft is connected to the shock, we will see very different time intensity profiles. For instance, for Western events on the left, we see very prompt signals as the spacecraft is well connected to the shock at early times. As it co-rotates away, we see particles decay. But as we move progressively toward connection points away from the shock, we begin to see particles increase that are less prompt and also second peak in the low energy particles, either before or after the shock, depending on the connectivity of the spacecraft. Well away from the shock, we see a slow particle increase in intensity and long decays, likely reflective of particle transport effects such as cross-field diffusion. The transport of SEPs in the interplanetary medium is governed by large-scale magnetic field geometry, but also by small-scale scattering from turbulence. Both the SCP intensity and anisotropy depend on the amount of scattering. Here we show the time intensity profiles and the deduced decay times for a number of SCP events measured by Pamela. What you notice is that all of the SCP events show a similar trend in energy, with the exception of two events, which is on the top here, which are Eastern Hemisphere events, and for which we expect significant cross-field diffusion. These trends can be extremely helpful in constraining the amount of scattering or the diffusion mean free path for SCPs. So depending on the degree of scattering, solar energetic particles may cross 1AU several times, and these multiple crossings need to be accounted for when determining the total number of SCPs produced in space. We can estimate the number of 1AU crossings using particle transport simulations and by comparing these to Pamela observations. In our study, we considered two transport models, a simulation based on the work of Cholet, 2010, and also a simulation by Bhattarbi in 2018. Both simulations assume an impulsive injection of monoenergetic isotropic particles at 0.1 AU, then follow the particles for 10 days, and both include magnetic focusing and scattering of an unspecified plasma turbulent field. The model of Cholet et al. Assumes one of two forms for the turbulence, uniform or one proportional to the gyrocyclotron radius. The predictions show the time-dependent development and decay of the intensity at 1 AU here. For instance, a short mean free path results in a long decay times. The degree of scattering is adjusted to increase or decrease the anisotropy and the associated decay time. So for our results here, the average number of crossings on the bottom here tends to be greater than 10, but depends on the choice of mean free path, of course. We also determined the number of crossings using a separate 3D test particle model, which includes the effects of a wavy heliospheric current sheet and solar magnetic polarity. The calculations show that the number of crossings does vary on the different configurations of the heliospheric current sheet and magnetic polarity of the sun. The number of crossings determined for a flat heliospheric current sheet with A positive polarity is actually consistent with the results we get from the model described by Cholet for a similar magnetic configuration. We also compared this simulation with the SCP time intensity decay observed by Pamela for the 2012 May 17th GLE event and found that the results were consistent with a mean free path of 0.3 AU. In computing the total number of protons in space, we had to make several important assumptions. The first is that we determined the spatial distributions defined by the proton intensities above 80 MeV, although the distributions are likely to be narrower at the higher energies that we're interested in. Secondly, we assume the same angular distribution for the latitudinal dependence as the longitudinal dependence. Finally, we model the scattering assuming a conservative mean free path of 0.5 AU with a wavy heliospheric current sheet, which gives a total number of crossings between 8 and 11. These assumptions lead us to derive upper limits for the total number of protons obtained at 1 AU. So here are our results. What we're showing is a comparison between the proton number from Pamela and the proton number derived from Fermi-Lat observations using a gamma ray production model. The Fermi-Lat results are based on the Scher 2018 work. Two things are notable from this comparison. The correlation is quite poor, and the ratio spans more than 5 decades of magnitude. The precipitation rate is shown on the right, which is the total number of protons, those that escape plus those that produce long-duration gamma ray flare emission, that are needed to precipitate back to produce this emission. I think it's actually a little bit easier to see it in this figure where we're showing the precipitation rate as a function of the event number. And what you can see is that only 5 events have precipitation rates below 3%, while the rest require a precipitation rate greater than 10%, and actually 4 require precipitation rates greater than 80%. So if we look more closely at these results, we notice a couple of important things. For instance, we see huge variations such as the May 17th and March 7th events, which differed considerably in flare proton number, but have similar proton numbers in space. This variation may be the result of sporadic and unpredictable magnetic connection between the shock front and the sun. But this widely varying connectivity isn't supported by the smoothly decaying long-duration gamma ray emission that we observe with Fermi-LAT. Furthermore, the particle number at the flare observed at the upper left with an 80% precipitation rate would imply a high energy population that is efficiently extracted from the shock and likely quenching the shock. Indeed, several of the events in this corner have been shown to have high shock formation heights, resulting in a weakening shock that make it even more difficult to efficiently accelerate particles above 500 MeV. Several of the SCP events measured by Pamela exhibit spectral rollovers above 100 MeV, even though there are abundant gamma rays above 1 GeV, suggestive of a particle population at the sun with a much higher energy rollover. Finally, there are long-duration gamma ray flares that exhibit high energy gamma ray emission but have no associated CMEs, and likewise, there are examples of fast full halo CMEs with no greater than 100 MeV gamma ray emission. Given these considerations, it's difficult to reconcile the back precipitation model in that this model does not pass what we call the particle number test. So in light of these conclusions, we consider an alternate scenario for the origin of long-duration gamma ray flares, which involves particle acceleration via the second-order Fermi mechanism and trapping within extended coronal loops where the ions diffuse to the denser chromosphere to radiate. The model consists of an initial injection of impulsive phase ions into a large magnetic loop of length L. Particles diffuse to the ends of the loop and precipitate in the dense chromosphere or photosphere, but they are also accelerated by the second-order Fermi process to higher energies. Essentially, we're considering a homogeneous and uniform trap, which isn't quite true, but still illustrates the basic physics. As such, the spatial diffusion coefficient in the loop, with loss at the boundaries, is given by a characteristic diffusion timescale, L squared over the diffusion coefficient, which I've already discussed, which L is the loop length and the diffusion coefficient is kappa. The acceleration timescale is given by the diffusion coefficient over the Alfvén speed squared and is proportional to the diffusion coefficient, such that the greater the diffusion coefficient, the less momentum diffusion. Note that the product of the two timescales is constant and independent of the diffusion coefficient. So the free parameters are the injection position within the loop, the ratio of the spatial timescale to the acceleration timescale, where the timescales are set by the varying loop length and the Alfvén speed. So finally, we pick the loop length and kappa from photometry, that is from looking at the intensity of the light as a function of time, and further constrained by other observations where possible. So this model was actually qualitatively used to explain the 1982 June flare long-duration gamma ray emission. The loop size of 100,000 kilometers, which is considerable size of the sun, and a mean free path in the range of 100 to 450 kilometers, consistent with the diffusion approximation. So we can test this theory with a few new examples of long-duration gamma ray flares from Fermi-LAT. One notable event is the March 7th event, which lasted 20 hours. It was associated with an X5 and X1 class flare that occurred 1 hour apart from each other. These flares were also associated with very fast CMEs and SCPs. Several of the researchers found that it was in fact only the first X5 flare and associated CME that was responsible for the observed SCPs at 1 AU. Also for this event, the spectrum softened with time, although there are cases where the opposite occurs. Finally, in the bottom of this plot, the centroid of the LAT emission was consistent with the flare location to within 10 degrees, but there is some evidence that the source of the emission moved westward over several hours, suggestive in our scenario of emission from the first flare followed by emission from the second flare, perhaps associated with a different loop. We modeled the 2012 March 7th flare in the context of the acceleration and trapping loop model. The blue curve is the model fit to the first flare and is consistent with a loop size of 1 solar radii, while the red curve is the model fit to the second flare with a loop size of 3 solar radii. The spatial diffusion coefficient is chosen to be the same for both loops. While other combinations of spatial diffusion coefficients and loop lengths are possible, it is clear that the large coronal structures greater than 100,000 kilometers are necessary for acceleration beyond the pion production threshold. I also want to point out the red arrow, which indicates the displacement of the LAT emission centroid and overlaps with the emission of the proposed second flare loop. Furthermore, the CME, which is associated with the proposed first flare and presumably responsible for the observed solar energetic particles, is nearly a half an AU away from the sun at this time. So we also modeled the emission of the 2017 September 10th flare. The model fit is in blue, that's just the blue curve here, showing yet again a smooth exponential decay with a time constant of 6,500 seconds. The event is particularly exciting because observations from the expanded Owens Valley solar array detected just one loop associated, not just one loop associated with the event, but two. In this figure, you can identify the relevant magnetic structures and their dimensions. There is an inner structure above which reconnection can be seen in the form of a current sheet, and that's shown as the figure to the right. There is also a larger structure that is highlighted in the middle figure with the red curves indicating likely legs of a single larger loop. Assuming a dipole geometry gives a loop dimension of 1.4 solar radii. We now have a reasonable measure for the loop dimensions that can further constrain the trapping acceleration scenario. So in the context of the Ryan-Lee model then, a 6,500 second precipitation of particles to the foot point in a loop length of 1.4 solar radii requires a diffusion coefficient of about 10 to the 17 centimeters squared per second, corresponding to a mean free path of 200 kilometers, which is again consistent with the diffusion approximation. To see how much energy is in the waves that we need for this model, we can relate the diffusion coefficient to the wave field energy density, assuming a Kolmogorov form, which turns out to be 0.7 ergs per centimeter cubed. Comparing this to the magnetic fields along the loop, we see that it is too large at the loop top, which is located at about 0.4 solar radii in this case. However, closer to the foot points, the magnetic field is much greater. We find that if B is about 10 Gauss, then only 18% of the ambient magnetic energy need be in the form of waves. And in this situation actually improves rapidly with increasing B in a dipolar field. Finally, equating the acceleration timescales with the diffusion timescale, we can infer a lower bound for the Alfvén speed of 140 kilometers per second, which is 10 times less than the commonly accepted value of 1,000 kilometers per second. In a similar study, Grechnev et al. Provided evidence through radio observations at Nancy that the behind-the-limb flare of 2014 September 1 involved two distinct quasi-static loops of different sizes with emission consistent with prolonged confinement and perhaps reacceleration. They concluded that a shock passage seeds the large loop in which diffusion process occurs. This event is similar in that the reconnection site associated with the central hard X-ray emission, AIA, and microwave image gives rise to a breakout process, producing a shock that likely accelerates particles to modest energies at low altitudes. However, after 3 hours, the region behind the CME will likely reconfigure into a more dipole-like structure. This would leave behind a large loop with seed particles, with those particles being unrelated to the impulsive phase. This is somewhat reminiscent of the Hudson lasso picture. On the other hand, there is also a study by Amodeo et al. In 2018 that found that the Fermi-Lat localization of this event to be consistent with the flare location over the entire 6 hours. They inferred from the temporal variation of the gamma rays that there were 3 phases of emission, with the last phase of the emission they concluded was more consistent with the phase originating from a CME-driven shock. Continuous acceleration is not new. Here I'm showing a few cases from the well-studied Compton Gamma Ray Observatory for the 1991 June flares, where we do observe a delay, but where we do not, observe a delay between the impulsive and extended phases, but rather witness continuous and progressive acceleration. The top figure shows the hard X-rays and the nuclear-related gamma ray emission at the start of the event, and indeed even some photons in the 8 to 30 MeV range. As the event progresses, the hard X-rays and low-energy gamma rays decrease, and the highest channel drops to background levels completely. The high-energy channel does not increase again until roughly 8,000 seconds UT. During all this time, neutrons, as detected in the 2.2 line, are steadily decreasing but exhibit an extended emission period similar to the pion-related emission. The gap in time between the impulsive and extended phase emission is simply a result of the transition in production cross-sections between the nuclear-related and the pion-related gamma rays. Even more illustrative figure of spectral evolution is shown in the 1991 June 11 flare below. We see the impulsive phase is delineated by the dashed line, as shown also to the left from the egret data. And we can observe 8 to 30 MeV gamma rays diminish after the impulsive phase and reach background levels for almost 10 minutes before increasing again during the extended phase, as shown in the blue arrow by the egret data for greater than 50 MeV photons. During this entire time, the solar neutrons are detected in the impulsive phase, but continue and peak again before the 50 MeV photons, indicative of the spectral evolution as the protons diffuse and also attain energy above the pion threshold. From observations such as these, it is clear that what we need is a model that can explain in a consistent picture how we can observe such continuous and progressive acceleration. And I think the Ryan and Lee model does a decent job of this, although more work is needed. So of course, the Ryan and Lee model is too simple as is. For large loops, we need to incorporate non-uniformity of the magnetic field. We also need to account for a variety of loss mechanisms, including collision and gradient drifts. Currently, the spatial diffusion coefficient, kappa, is independent of the energy and position, making the momentum diffusion proportional to p squared. We also need to further investigate the loop dimensions and its relation to the coronal mass ejection and the stability of the loop during the eruptive process. We still need to figure out how to maintain the appropriate level of turbulence in the large loop in order to accelerate ions to greater than 300 MeV over many hours. To address this, we could investigate self-generated waves produced by the low energy protons that resonate with the higher energy protons to produce a non-Kolmogorov spectrum similar to that computed by Lee. Finally, we need to include a momentum-dependent diffusion coefficient that can reproduce the varying power law spectral index that we observe in some of these events. So there are definitely remaining challenges to both scenarios. In the case of the back precipitation scenario, we need to be able to explain the smooth exponential decay of high energy gamma rays and relate this to the possible paths the particles can take back to the sun. Of course, we also need to understand why we see such wildly discrepant numbers of particles estimated in space and at the sun, and where some events actually require 80% precipitation. In the case of the Ryan and Lee model for trapping and acceleration, I discussed some of the challenges in the previous slide, but suffice it to say, we need to somehow maintain the wave field for hours, and more work has to be done in identifying these large coronal loops. So in summary, the long-duration gamma ray flares are one of the most energetic processes at the sun and pose significant challenges for modeling given the high energies and prolonged emission. Based on recent comparisons with Pamela covering the energy range of interest for studying long-duration gamma ray flares above the pion production threshold of 300 MeV, we conclude that the number of protons observed in space is not correlated with the number of protons that we need to produce the long-energy gamma ray flare emission. In fact, we observe large variations where the ratio spans 5 orders in magnitude. Precipitation rates place challenging constraints on the CME shocks as the source for long-duration gamma ray flares. An alternative explanation for long-duration gamma ray flare emission is coronal trapping and acceleration, which decouples the SCPs from the interacting protons, and where the effects of diffusion are consistent with smooth exponential decaying gamma ray light curves. Recent observations support the existence of large persistent coronal loops, and modeling efforts are promising. And that concludes my webinar. Thank you.
Okay, thank you, Georgia. Very interesting, very nice presentation. Now we are open for questions. So if you have a question, please unmute your microphone and ask or make a comment. So far, all microphones are muted, so this gives me a possibility to ask my question. I wonder, so I see that there, in fact, there are many gaps in our knowledge, in our observation of these gamma ray events. But could you somehow classify or prioritize what are the still main unknowns which have to be filled first?
Yes, I mean, I think the things that would really help to solve this problem is, to be able to better image these larger loops somehow. Obviously, we need to get a handle on how to look at the turbulence, whether there's turbulence in there. Is the turbulence homogeneous throughout the loop? So, I think those kinds of things would be important. I think also just connecting it back to the impulsive phase emission and what's actually going on in that impulsive phase. I really would like to see measurements of solar neutrons. I'm a little bit biased here since I'm building instruments to do that, but that would help us to bridge the gap that we're seeing, which may lead us to believe that there's really a delay when in fact, I think we're seeing continuous acceleration. So I think adding that data set would be helpful too.
And a minor question, in terms of composition of SCP and gamma ray producing particles, do you see any correlation? For example, if you observe helium-3 rich SCP, you also have helium-3 rich local flare particles, or there is no such correlation?
Well, ideally, yes, we'd like to say we do, but to be able to measure them, it's very difficult because typically the helium-3 rich events are impulsive events, which is not the same as the impulsive gamma rays. And so those solar energetic particles tend to be, as you know, very small. And typically we either don't see those gamma rays or we can't measure them because we don't have the sensitivity. So that's the first problem. We do, however, have some studies by Murphy et al. Where we can see a hint of some presence of helium-3 in these larger long duration gamma ray flares that suggest there could be a presence of a seed particle population that may come from these more impulsive SCP events. But at the moment, we can't really do a one-to-one correspondence between those measurements.
Okay. Any question for other people or comments? Yeah. Yes, there is one unmuted microphone, so please go ahead and ask.
Hi, this is Sylvia. Hi, Georgia.
Hi, Sylvia.
Hi. So I was very interested by your idea that the impulsive and extended phase might be related to different processes of gamma ray emission. And
Yep.
yeah, and I was just wondering if more work is also needed on the theory side in the understanding of the gamma ray production, or if the only missing piece is just experimental, as you were mentioning.
Well, I mean, I think part of the issue is that we need to, be able to get a better handle on the energies, for instance, that are attained in the impulsive phase versus the extended phase. What is the maximum energies? Typically, we don't see the gamma rays reaching as high energy GeV energies that we do in the extended phase. So, and that of course relates to the time scales that we probably need to get those energies, to get up to those energies. So I think that somehow being able to model an event, one scenario could be that you get injection and somehow the impulsive phase is related to the, initial injection, and then very quickly we see something, but then the particles diffuse throughout this loop and take a much longer time to precipitate down. And so that kind of modeling we need to do a little bit more carefully.
Yeah. Okay, thanks.
Yep.
Other questions? So I see that all microphones are muted now at this point, so this means that we can conclude our meeting. And thank you, Georgia. And next one will be with Mark Chung in 4 weeks about his modeling efforts. Well, thank you very much for joining.
Bye.